of this delightful conference. Just quickly to remind the rules, there are only short questions during the talks, and longer questions are after both talks, after the end of two talks. And I don't remember if there are talks in between if there are questions in between the two talks.
You can ask quick ones.
You can ask a quick question after first talk, but longer question both talks. So the first speaker today is Moty Heiblum, and his title is "Does short noise measure always the quasiparticle charge?" Please, Moty.
Okay, thank you very much. Can you hear me?
Yes, it's all good.
You hear me okay?
Yes, we do.
Okay. So I want to thank the organizer to invite me to this particular conference. Next week, we have another one on the quantum Hall effect. And I'm always delighted to share our experiment in the quantum Hall effect because this is a major part of my work. I'm just starting to show you a trace sent to me by Janendra Jain. And you can see how he called it. And it's really a beautiful trace. And each of these peaks and valleys has a whole new physics inside it. So I want to concentrate now. Of course, the grower here are the most important one. Lauren will talk a little bit after me also, but he's responsible, if not to this particular one, but many other, this one too. I'm sorry, this one too. His name is at the bottom. Anyhow, I want to talk about short noise. This is one of the most important experiments for me that I did early in my career. So we follow basically the paper by Kane and Fisher suggesting to measure short noise. And via this to measure the fractional charge. And what I want to show you now is that the title is here, does the short noise always measure the fractional charge? Okay. And there are, along the talk, there will be quite a few names of my students and collaborators. So I'm not putting them all in because I'm going to show you data that spans more than 15 to 20 years almost. But I will concentrate mostly on the last one, on the last data results. And the three names at the bottom, which is Raj and Shurab and Hemanta, were the one that triggered basically this experiment, this talk, because they made experiment in the last couple of years on this issue. Okay, so first of all, just one transparency is on short noise, which most of you know. But if you have a full edge, what we call sometimes looking on a plateau of the conductance plateau or a plateau in a quantum point contact, there is zero noise. Of course, the people that are doing photons are envious. The Pauli principle makes all the electrons being in order, or all the quasiparticles being standing like nice soldiers and giving zero noise. And we partition it here to get noise, and that's the noise that we measure, okay? And that's what we call short noise. The particular realization is a quantum point contact that you all know, and we inject some hot current here, we partition it, we measure it at an amplifier, and the amplifier measure the voltage noise between this contact and the ground. So the current goes around, and the resistance here is E square over H, or the quantum Hall resistance. That's the big advantage, that even though I play with the quantum point contact, change in transmission, the amplifier sees always the R Hall. And this is flat noise, in particular at low frequencies. And the formula without temperature correction that I will address mostly is this 2EI that we know. I put a Fano factor in front of it. That Fano factor times E sometimes give us the fractional charge. That's the current, that's the transmission of the quantum point contact. We measure not at low frequency, very low, but we measure at a megahertz or so, when the 1/f noise is quite small. Okay, and this is just an example of one of these curves. This is just electrons. We measure electrons. You see, it gives us very nice data here. And this is what I will call, I will use a lot the word Fano factor. F is equal to 1, okay, in front of the electron charge. Okay, so the point is that we all know that the edge mode has some own properties due to the bulk edge correspondence. And I'm going to show you soon that take it with a grain of salt, okay? So again, the hot mode comes in, the edge mode carries a conductance of E square over H times the filling factor. I can measure the noise at the reflected part. I can measure noise at the transmission part. And the backscattering here is between the hot mode and the cold mode that come from ground. And here now you have partitioned one. Of course, this is anti-correlated to this because the sum of these two noises is supposed to be 0 because there is 0 noise at the edges. So here I go back in history, 1997, when we made our first measurement of E over 3, and the group of gladly measure E2. And as you can see, what I want to point out that we measured it, we didn't know how to cool down the electrons very much. We measured it at 50 millikelvin, gladly or measured it at 25 millikelvin. And indeed, we got a Fano factor of 1/3, as expected, okay? Everybody was very happy about it, okay? We were happy too. This is the two transmission, just to show you. The rounding here is because of temperature correction, which I didn't show you. And a year later, the reason that we did the other experiment at filling factor 2/5 because some scientists say, well, you measure 1/3, maybe you measure the filling factor of the bulk. So we went to 2/5 and we measure in 2/5 at high temperature also, and we measure and we got Fano factors 1/5. Everybody was happy. So the charge was E over 5. Now, let me just remind you about some of the edge modes, okay, that exist in the system. I must show you because it will be involved in the rest of the talk. Okay, so for particle state, we know that support downstream chiral modes. All of them are charged, okay? And then the electron hole conjugate states like if 2/3, 3/5, the stuff between 1/2 and 1, and also the non-abelian states support topological upstream neutral modes in equilibrium, okay? So we have this neutral mode that if you just measure conductance, you never see them, okay? But you will see they are important, they're very, very important, okay? And then we have also edge reconstruction that adds modes on the side, counter-propagating modes many, many times. And we find them prevalent in most of the states that we are measuring. Most of the states that we are measuring, probably due to a relatively soft edge potential. Okay, and this will be also very important. Now, a little bit more of the neutral mode. You may have neutral mode, but to measure them, you have to excite them, okay? So first of all, let's go back to 1990. McDonald suggested that the 2E over 3 was a full Landau level and 1/3 hole sitting on top of it, which is depicted here, okay? And again, Ken Fisher and Polchinski came up and said, well, we have an equilibration, charge equilibration between the charge E and the E minus 3. And the result is that you have now 2E over 3. This is the non-conductance and a neutral mode, okay, that are presented as electron and hole, okay? And then this upstream neutral mode is a topological neutral mode. I mean, because the thermal conductance of this system you see is 0, I'm not going to go into it because there is one conductance going back, one conductance to the front. So if I have one conductance here, I might have to have something that goes back, and the thermal conductance is a 0. Okay, but there were other configuration also suggested by Yigal Meir a bit later that says that if the potential is soft, then instead of having this picture I showed you before, then you have another reconstruction. You have a reconstruction of the edge, and you have counter-propagating 1/3 and 1/3. Indeed, he was right. That's what we see all the time now, okay, in our gallium arsenide samples. If you combine all these things in the red circle here, you get a charge of E over 3. Okay, I'm sorry. This is these two, the E and the E over 3, change now to be 2 E over 3s. Okay. So you have here, if you combine this plus this plus this, you have E over 3, and there is another downstream E over 3 here. So the final result is 2 charges of E over 3 and E over 3, but you need kappa or thermal conductors to be 0. You need 2 neutrals to go back. And this is the E over 3 configuration that we see in our system. Okay. So now you see it right away if you take a quantum point contact and you change the transmission. So here we are sitting, given an example, I'll come back to it. You see an 2E over 3, okay, conductors, and then you pinch it off and you see a beautiful plateau. We saw the first plateau years ago. We didn't know where it come from, okay? And then what it means that you have 1/3 going through and another 1/3 going back, and there is no partitioning at all of charge, okay? So we'll come back to it soon, okay? Now back to the neutral mode, you have to excite them. You have to put some energy into this neutral mode in order to measure it. So if you just look, for example, this is the chirality of a system. You have here a source and you have a ground. And at the backside of the source, you have a drain of some kind, okay? So the neutral mode going counter-propagating, counter-propagating into an amplifier. How are they excited? We know that at the backside of the source, there is always a hotspot. This was shown by von Klitzing, I think 1992, okay? That always at the backside of the contact, you have a hotspot, and the neutral, upstream neutral mode going in the opposite direction to the chirality of the charge is being heated. Basically, it takes energy from the neutral mode, and that's what we measure in the amplifier. So we are measuring the upstream neutral mode by measuring shot noise in upstream direction. And here is an example. This is the 2/3, okay, contact, and you can see a plot, okay, of the neutral mode of the noise versus current. And this is the topological one. It's very difficult to kill it. You cannot kill it. If you go to 1/3, where you are not supposed to have any neutral mode at all, you do have because of edge reconstruction. But if you look at it, you see here that this value is 10 to the minus 30. This value is 10 to the minus 29. So this is about 20 times smaller than this. And if you go long enough away from the hotspot, this will disappear. So this is, you have these modes that are gapping each other. The two 1/3 will gapping each other, and they disappear. So I call it non-topological. Okay, here is just an assumption how it looks like. Rather than 1/3, then you have 1/3, and there is something else here. I don't know what is the filling factor here. It might be dependent on the details of the edge, if the edge is soft enough. But these two will gap each other at long distances. So the same I want to mention that we measure also neutral mode at 2/5 state and many, many more states. Okay. So now just to tell you, see the difference between the topological and the non-topological. So here look, for example, on the 2/3. The 2/3 is topological. You cannot kill it. So if I go now with the gate voltage at the edge of the sample, and I put a very negative gate voltage, I sharpen the potential a lot, you see that the noise that I measure upstream saturates. It's excited less, it carries less energy, but it saturates. If you take the 1/3, I kill it. Okay, the neutral mode disappears, okay, almost totally, just by sharpening the edge. So you see, it does not, the neutral mode must not stay in neutral in 1/3. It depends on the details, and possibly many other filling factors. It depends on details. Okay, so now let me talk about unexpected noise. Okay, past and new measurements. So look, this measurement was done by Yun-Chul Chung. Okay, you see it's quite a few years back. And this is the 1/3 measurement. Of course, it's much better than the measurement we did initially with some 50 millikelvin, 80 millikelvin. The scatter of data is better. This is get when the transmission of the quantum point contact is about 0.99. Okay, the value is extremely small because we went all the way to almost open quantum point contact, not to have any bunching or anything like this. So the Fano factor was 1/3. But now, if you go now to 2/5, this is a busy slide. Take a look. This is at 82 millikelvin. We have this noise here. And when we cool down to 9 millikelvin, we have this here. And if you plot it in between, the Fano factor down here is 1/5. Very much like we measure it at the beginning of my career. But if you cool it down to 9 millikelvin, I couldn't go below this for electrons, it's 2/5. So the Fano factor is the bulk filling factor. And the charge is E/5. Okay, let's go on. So this is an early experiment that was published and most of the time not seen by anybody. And if you go to 3/7, okay, then again, here the Fano factor is 1/7. But when we cool it down, we were stuck at 2.47 because probably 9 millikelvin is not enough. I assume that it was on its way to be 3/7 rather than 2.4/7. Okay, lower temperature probably is needed. So the Fano factor is approaching here the bulk filling factor. Now, what about whole conjugate states? Okay, this I show you particle states, okay, that definitely has an upstream topological neutral mode. There is nothing you can do about it. Okay, so I'll give you a couple of examples. So let's go back to the 2/3. Okay, this is the electron hole conjugate state. This is a plateau. This is the one I showed you before. But what happens here, what happened on the plateau here? Okay, what happened on the plateau has noise on the plateau. Okay, this is the noise on the plateau that we measure. How come we have noise on a plateau? There's no noise, right? There is 1/3 going through, 1/3 is scattered back, nothing is partitioned, and there is noise. Okay, but there are neutral modes. So the neutral modes, okay, the noise must result from neutral modes. Otherwise, there's no explanation for it at all, and I'll show you more. So let's go now on plateau, no charge partitioning, okay? Away from the plateau, you have charge partitioning and you have also neutral mode. Both participate, but I'll show you an example which is simpler to see when we look on the plateau. Again, this is the 2/3 I showed you before. That's the plateau, half plateau, half of transmission. And then you go and you measure also the Fano factor here, not on a plateau. Again, you get the same Fano factor. So again, at filling factor 2/3, we measure here only neutral, that gives us 2/3 Fano factor, 2/3 Fano factor. And here we also measure. So they play together again. If the charge gives you more, the neutral gives you less and vice versa, okay? Now, you can see also, again, if you warm it up, you go from Fano factor of 2/3, you go to Fano factor of 1/3. Okay, very much like the 2/5 business and the 3/7 stuff. Okay, but give you more example on whole conjugate state. All of them has neutral mode that we measure. They have it and we measure, but this one also is highly reconstructed, but it must have neutral modes. And here is the transmission through the quantum point contact of the 4/7 device, okay? And there are plateaus. There is a plateau here, there is a plateau here, the plateau here. And we measure on each of these plateaus. Charge partitioning does not take place at all. And each of these plateaus, the Fano factor is 4/7. Okay, so the plateau gives you anywhere you sit here, you sit here, you sit here, you get again this Fano factor of 4/7. Similar thing happened at 3/5. That's another whole conjugate state. You have a plateau here and you have a plateau here. You get Fano factor of 3/5. You don't get the 1/5. The charge is expected to be 1/5. The charge expected to be 1/7. It is not. It's the bulk filling factor. But also at filling factor 1. At filling factor 1, okay, look again on the transmission. I'm not saying that this is universal because filling factor 1, what I show you now is non-topological. Okay, it doesn't have to have any neutral mode. Okay, because the kappa, the thermal conductance, is unity. So if you go here and you pinch the quantum point contact, you have a plateau of 1/3. The plateau of 1/3 suggests right away that the 1 breaks down to 1/3 and 2/3. And if you go and measure the noise on the plateau again you measure, but now what do you see? Fano factor 1, the bulk filling factor. Okay. So if you measure, you want to make sure, are there neutral mode? Yes, there are neutral mode. And this is, we published it. Okay. So on the 1/3 plateau, you have Fano factor 1. I want now to take you even to something that's a bit more crazy or more complicated a little bit. Okay. So let's now detach the edge mode from the bulk. Namely, let's forget about bulk edge correspondence. Okay, it's gone. How do I do it? Okay, rather than looking at edge mode, I'm going to invent new modes, which I'm using it for other purposes already for the last couple of years. Interface mode instead of edge modes. What do I mean by interface mode? Let's now have a bulk, a gate in the middle of the center. Let's say we are here at filling factor 2. We like to call it C, okay? And then here we put a gate and we call it a boat, right? It reminds you of a boat in the sea. And if I put on the boat a voltage, a gate voltage, and deplete to filling factor 1, okay? Then this is pictorially showing what will happen, okay? The interface mode will be 1, okay? Or outside you have the filling factor 2, and here at the interface between 2 and 1, you get 1. Okay, so this is what I call now an interface mode. Okay, and the reason it's so beautiful, first of all, you can invent many modes by all kind of differences, which are not necessarily the same mode as the edge mode and don't have even the same central charge. Okay, because there are different between two bulks. Okay, there is no bulk edge correspondence because there are two bulks here. Okay, so this particular edge mode allows us to do all kinds of tricks. Okay, so let's now try to see what is now the noise if I look at the system, which I call it a symmetric quantum point contact. Okay, so if I now make a bulk filling factor of 1, and the two outside, which are usually vacuum, right? Usually I have 1 and a vacuum here and a vacuum here, okay, depleted on both sides. Here, I don't have vacuum, but I put 2/3 on both sides. So the interface mode is 1/3, right? It's 1 minus 1/3. And now I'm measuring the noise of this 1/3 conductance mode, scattering from here to here and giving me noise. And that's what I wrote, 1 minus 2/3 gives me 1/3. And the Fano factor is 1. You see, okay, so I measure Fano factor of the bulk, even though the edge mode is doesn't much know about the bulk, okay? It's just a liquid that moves around, okay? If I go now, this is a symmetric UPC. If now I go now to asymmetric one, okay, I'm sorry, asymmetric is the next transparency. I am still symmetric, going in more examples. So here is 2/3, and I have 1/3 outside, instead of 1 and 2/3, 2/3 and 1/3. Again, it's 1/3, similar mode to this guy. But again, I look at it, okay, filling factor, 2/3, Fano, 2/3. And the third example is when I go now to some weird state that we find it nicely quantized, and I have here 2/3, 415, and the interface is 2/5, and I measure the noise, and I get 2/3. Okay, so I measure the Fano factor, independent of the edge mode. Okay, and now I'll go to asymmetric state, okay, asymmetric quantum point contact, okay, and now I have here a different on, if I call this a C and this is the boat, or the either way around, I don't care now. If this is filling factor 1, and I put here 2/3, and I put here 3/5. So the edge mode here is different than the edge mode here. And I scatter from here to here, and I get 1. Okay, I get 1, the bulk. And this one is even crazier. Now I go here and I even don't quantize this region at all. This becomes sort of like a lousy metal. Okay, so now I plotted here edge mode, but there are no edge modes here at all. And I scatter from 1/3 through the bulk into unquantized region. And again, I get close to 1. Again, bulk. Okay, so these few examples show you how universal is this shot noise, which in all these cases doesn't give you, or in many of these cases, does not give you the fractional charge. It gives you the bulk filling factor. Okay, and here toward the end, I just want to show you how can it happen. And this is in a way a hand-waving explanation, and this paper was published by some of these authors here. Okay. So I'm taking the simplest example here. Let's go to the 2/3 state. In the 2/3 state I showed you before is 1/3 and another 1/3, okay? And this is the 1/3 going, this is filling factor, this is half. Filling factor, 1/3 goes here and 1/3 goes there. And then the cold one, you can see the cold one going around like this. And here the other one reflected. And now the hot and the cold now are equilibrating. Okay, so now I equilibrate and generate now and excite this neutral mode going upward. So here the neutral mode is not excited by the hot spot, but it's excited by equilibration between the hot and the cold mode. Okay, so now if you have now these neutral modes coming here, they come around here because this red one do not give you any noise at all. They just go freely on the plateau, no noise at all. But these ones, okay, are fragmented here to particle hole state. Particle hole, this particle hole, and these have been calculated and shown exactly to give you 2/3. And if you move away from the plateau, then you have a combination of charge scattering and neutral mode fragmentation. Okay? And this gives you exactly 2/3 Fano factor. And there are more examples that all of them can be explained by counting beams, if you wish, by counting particles that are scattered from cold to hot across the quantum point contact, or in addition to neutral mode that we find in all our states so far. Okay, so that's what I call it. I'm finishing now. I think I'm pretty much on time, even in the 25 minutes or so. So this is what I call the magical proliferation of neutral mode. Okay, that had been explained in more than one paper by this group. Okay, so partitioning of charges plus fragmentation of I don't know what is EPF came up here, of neutral mode, fragmentation of, this is supposed to be of a neutral modes, gives you that the Fano is the bulk filling. Okay, the Fano will be quasi-particle charge at a higher temperature, and we assume that because the neutral mode decay as the temperature increase. This was measured too. I didn't show you data. When you increase the temperature, the neutral mode decay faster as it goes along. It could be the reason that the neutral mode slowly disappear, and I measured the quasi-particle charge. And we were lucky in 1997 to work at high temperature. Because if I would measure 2/5 and I would get 2/5 rather than 1/5, well, I don't know, there would be some problem. Okay, so I didn't know how to cool it. We didn't know how to cool it, and that's what we got. So I'll finish by this. The bulk says it all. Okay, and the point is that I think there should be some fundamental reason that this should happen. Some fundamental reason that forces the Fano to be the bulk filling, and not by counting electrons going from here to here and counting and adding fragmentation and electron, etc. There should be some fundamental reason for this, which I call anybody that listens to me now, maybe they can think about it. So thank you very much.
Thank you, Moty, for a very nice talk. So since we burned, you can go ahead.
So, hello, Moty. Very nice
Hey,
talk.
Baron. Hi.
I would like to make one remark, at least in the case where the charge of the fundamental quasiparticle agrees with the bulk filling. What you observe is very natural, because the bulk determines which charge is being scattered, right? The bulk quantizes charges and not the edge. So say if you have an integer bulk within arbitrary edges or metals, it's very clear that electrons will be scattered because the bulk determines the particle which is being scattered. So the observation becomes extremely interesting and non-trivial if the fundamental charge is different from the bulk filling fraction, as you pointed out in the case of 2/3, 3/7, and so on. But the integer bulk within your ocean of different fillings, I think that's rather to be expected, that would be an electron charge.
I totally agree. But note that if you look at the reconstructed one that I showed you, it has reconstructed to 1/3 and 2/3. You go now to transmission of 1/3 in the bulk, because what you say is correct when the bulk and the QPC are approximately at the same filling factor inside the QPC. But here I'm showing you that the bulk is 1, the QPC is at 1/3, and still you get filling factor 1. You get Fano 1, even though you don't.
Yeah.
This is it. Okay, so this is an example. Okay, yeah, but you are right what you say. Yeah.
Okay, Janet, I see you raised your hand, but maybe let's keep your question after the second talk to stay on schedule. Is Andrea Capelli there?